it's so unreal. Oh, it's so unreal. Baby, don't you cry for me. It's an illusion, just an illusion. I thought I knew what life should be. It's an illusion, just an illusion. Critics crucify your latest show. Another drink and then you lose control. And then on stage I feel a fire burn. There is no return. I'm always on the run. I give it to you, babe, with all my heart. For it's not too late. Oh, it's not too late. Baby, don't you cry for me. It's an illusion, just an illusion. I thought I knew what life should be. It's an illusion, just an illusion. Baby, don't you cry for me. It's an illusion, just an illusion. I thought I knew what life should be. It's an illusion, just an illusion. I've been told about living like a star. Hotel rich champagne.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
All right, so today we are going to continue our series of discussion on how to optimize our code for memory hierarchy. And in the meantime, we are going to introduce a new concept called virtual memory, which I put a subtitle, Just an Illusion, which is exactly the same name of the song that I played before the lecture. And through this lecture, you will probably learn that a lot of stuff in our computer system, we are just creating illusion to the programmer. So one of the illusion that you have previously learned is the instruction set architecture. And the lecture today will tell you that even the memory is an illusion. But before we start, it's always important to remind you where we are coming from. And the most important big picture throughout the computer architecture class is that don't forget, you are using a volume computer in a way that, well, your program is compiled, and then when you want to execute a program, everything has to be presented in something somewhere called memory before we can execute the program. And even during the execution, the processor has nothing about the processor know nothing about your program. The processor can only do one thing, that is first fetch the instruction from the memory. And whenever you have a data memory access, encoded in the instruction, then that's when the processor would additionally access memory. So saying that if you have an instruction count saying the instruction count number as IC, and on average, if each instruction would occur 30% of the data memory access, then it means that you will have to generate the instruction count instruction count times 130% of the memory accesses, because every instruction is essentially coming from the memory. And because every instruction is coming from memory, also data are coming from memory. So it's really important that we have to make the memory subsystem efficient, especially in the era where we are now, processors are 100 times or 1,000 times faster than your DRAM. So our solution is that we built memory hierarchy, which we place several levels of SRAMs between your processor cores, which operating at 2 to 4 gigahertz, or say the cycle time is less than a nanosecond. And between the DRAM, which your cycle time is probably tens of nanoseconds, like 60 to 100 nanoseconds, to bridging the gap between the performance. And with this multi-level cache, what happened is that your processor would always consult your L1 cache, no matter it's instruction or data. And in your homework, you already learned that in the L1 cache design, we typically have a split data and instruction cache, and that's because the locality of code and data is completely different, as you could imagine. But no matter it's instruction or data, whenever you need something, it has to be from the L1 cache. And if the L1 cache has the stuff that you want, it's a hit. If the L1 cache doesn't have the stuff you want, it's a miss. And how do we know it's a hit or miss? First of all, your cache will partition your address into tag, index, and offset. And we use the index to figure out which set of the cache to look into. And each set will contain one or more blocks. And we compare the tag to see if the tag that is currently in the block is equivalent to the tag that you are looking for. If that's the case, that's the hit. Otherwise, it's a miss. And if it's a miss, then we have to figure out if we have space in L1 cache to place the block. If not, we have to select a victim block. And the victim block sometimes is dirty, meaning that the data is modified. So you have to write the data back. And by writing back, we mean we present a change to the next level memory hierarchy. And then the same thing would occur again in L2 until we find out where our block is. And the procedure of writings are essentially the same as reading, except that during the write process, we present the word that we are going to modify in the L1 cache. So that's the stuff different from reading and writing. So to know how to partition your address, I already introduced the formula C equal to ABS, where C is the capacity of your cache data array, A is the weight associativity, B is the block size, and S is the number of set. With that, the number of bits in block offset would be log 2B. The number of bits in a set index would be log S. And the remaining bits in your address, in your memory address would become the tag. And with that, you can actually simulate the behavior of your cache before really putting into practice. And then one thing you will find for this pieces of code, with an NVIDIA Tegra X1 processor, it turns out that everything is a miss. So the cache performance of these pieces of code is really bad. And there are many, many chances that we would interface the situation that your code behavior looking really good to from the programmer's perspective. In a way, it's easy to read. However, that's not easy to execute. So it turns out that in terms of loop, we have several different optimizations that you may apply in your code. The first one is change the loop index to iteration, the order of iteration, to make sure that the order you iterate through your objects are fitting the spatial locality of your cache. The first technique is called loop interchange. And the second technique is called loop fission, that basically remedy the problem that we mentioned in Tegra X1 in a way that instead of having an iteration through all the data structures we have, we separate the iteration into two different loops. And it's going to give you the same result. However, you can eliminate most of the cache misses. And finally, well, for caches like Intel's processor, it can accommodate multiple ways. Then you probably prefer a different direction of loop fission that's called loop fusion, in a way that we try to combine multiple loops together so that we can reduce the amount of overhead in instruction count and control overhead. So these are the optimization that we learned from the last lecture. And now let's going to see more case studies of software optimizations in memory hierarchy. And then I will introduce the concept of virtual memory. And finally, we will talk about the essential architectural support for virtual memory. So another algorithm, or say another optimization that I will introduce is called blocking. So for blocking, we are going to talk about an algorithm that is intensively used nowadays in AI machine learning. That's called matrix multiplications. So the basic idea of matrix multiplications is like that. We have 3 arrays, and each array will contain the data you want. And 2 of the arrays, or say 2 of the matrices, A and B, they are the input and C is the output. And to calculate the result, you have to multiply a column and a row from from both input matrices, and then accumulate the pairwise multiplication result into a cell in your result array. So the naive implementation of matrix multiplication is an uncubical algorithm like the left-hand side of the slide. And it's uncubical, so it's probably not too, it's probably trivial for you that, okay, so if I have a matrix multiplication code saying that, okay, let me see. If I tell you that I have a matrix multiplication code that's originally running about saying like 8 seconds, you would imagine it would take 24 seconds. Or if it takes 2 seconds, you would imagine it would take, sorry, if it's uncubic. Okay, so saying that, okay, if I have a matrix multiplication saying that my original matrix dimension is 1K by 1K, and if I say it runs about 2 seconds, and if I say today I expand the matrix size by twice, saying that I'm going to do 2K by 2K matrix multiplication, then you would imagine the execution time to be 8 times. But is it really the case? So let me show you this demo. So here I have the matrix multiplication code where I have some part of the code that I try to initialize the matrices. And also I have the MM function, which try to perform the matrix multiplication. And now, one thing I would do is that I would, okay, let's do this. Okay, now I compile the MN code with -03, which meaning that you have already learned it's highly optimized. And now let me run this code for 1K by 1K matrices. And then you will see, well, it takes 1 second. And as I say, if I want to do 2K by 2K matrix multiplication, it's probably, you will probably say, well, it will take 8 seconds according to what the algorithm teacher tells you. But let me see, let's take a look and see how true what the algorithm teacher is telling you. And now I believe when I say this old stuff, not sure it makes sense to you, but you can probably feel, it should be more than 8 seconds, right? So Yeah, looks like the algorithm class is not really that useful. And as I keep mentioning, and it turns out that what algorithm teacher tells you is far from real, because algorithm teacher tells you that it would probably take 8 seconds, but here it takes about 30 seconds, half minutes, which is 30 times slower than what is supposed to be from the algorithm's perspective. So, algorithm class is totally broken. So, so this is what happened, right? So, in real, that, well, again, algorithm class always assume that you have a perfect computer, the cache never misses. But after the lecture, you should learn that, well, for 2K by 2K matrices, right? Each row itself is already 16 kilobytes. And remember, we have, for example, like the processor that I'm using right now is an Intel processor with 32 kilobyte L1 cache. So 2 rows is already good enough to fill all the cache, So remember, for each iteration, what we want to do is that we actually take the whole row, multiply another column. So when you perform an iteration, what would happen is that even though I want to get this one, and let's assume we can put this one in the register, we forget about this. For each of this is 16 kilobyte. And for the column, it's even worse, right? Because thinking about, remember, we are when we align our matrices, is row major order. So for each column, actually, depending on how many elements you have to fetch this many blocks we have. So if you have a 2K by 2K matrices, then each of this would be a separate block. So you have to fetch 2 kilobytes times 64 byte data into your cache. So consider that. You will figure out that, 2 kilo times 64 byte data. So it will be 128 kilobytes of data set when you want to perform this iteration, which is almost impossible to fit into your 32 kilobyte cache. So then, it's no doubt that these pieces of code, they have very, really bad behavior of memory performance. So, and even though in the next iteration, I claim that, well, I reuse the same row. However, thinking about that, it's 128 kilobyte of data. So it's very unlikely this 16 kilobyte of data could be kept in your cache because of the capacity you need for this, right? So it turns out that if you keep going, you will figure out that the whole matrix multiplication code is actually cache misses all the time. So again, we can use the block algorithm. We can use the tool called Valgrind to figure out the matrix multiplication performance of the code. But however, as you could imagine, it takes about half minute to finish that. So and Valgrind also needs some more profiling information. So I don't want to run this demo in the class because it's really, really slow at this point. But you should have an idea that, well, it's really, really inefficient because of the behavior. So to remedy this situation, in your textbook, we introduce another kind of implementation of matrix multiplication. It's actually the right-hand side. When you see this right-hand side, you will probably feel, oh boy, it's going to have more for loop, more instructions, more divisions, and the code seems very hard to read. I don't want to do this, right? But if you look at the performance of this code, it's actually really good. So let me show you the implementation of this code. So this is exactly the same program, in terms of initialization. The only thing that is different is that instead of calling the mm function here, I'm calling the block mm function. And if you look into the detail of the block mm function, it's indeed implementing the stuff that we just mentioned. So I already compiled a program. And okay, so for this program, I do have another argument saying that I want to partition a block into how many different pieces. So saying that right now, I am running the 2K by 2K matrix multiplication, and I want to partition the matrix into 128 by 128 tiles. Then let's see how much time it would take. So originally, it would take 30 seconds to run a block MM. But now with this, it only takes 6 seconds, right? And then you can also test. If I run it with 1K, it's only 0.6 seconds, still faster than the original implementation, the naive implementation of the matrix multiplication. And the other thing that you might find is that the speed up, or sorry, the slowdown of scaling up 1K to 2K is pretty close to 8 times. So what that tells you is that your algorithm teacher is correct only if we can eliminate most of the memory misses. So, but why the block algorithm can be really effective? So if we take a look of what's happening in the block algorithm, it's actually every time, instead of go through the whole column and row, we only go through part of the row and part of the column, so that we restrict the range of computation every time. And then gradually, if you want to finish the computation of this cell, it will go through the next tile at some point. So that's why so every time you can consider that I'm only operating on a small time. So now I want you, so every time your cache only need to hold this submatrices in your cache. So now I want you to go through these pieces of code and think about what's the benefit of using block algorithm and what kind of cache misses do we remove? All right, looks like everyone has the boat in. So looks like we do need some kind of discussion after looking at your results. So why don't you guys go into groups, and then we can come back in the lobby whenever your group finishes discussion. So go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Okay, time is up. Okay, so looks like after discussion, we do have an answer that's more popular now. And who raised their hands? Okay, so Ewan, can you share your thoughts with us?
Yeah, our group thought is like we want to choose the C or D because we can make sure that the conflict myth can be removed since the side like in this way we can have more space to save the tag, but we are not sure if the capacity myth can be removed. In my opinion, that the capacity can be removed because like we can have more space to save. So I think the capacity myth can be removed.
Okay, so say again. So why do you think the conflict myth could be removed?
Because we can save more tag in one index.
Are you able to store more text in one index with the code modifications? How does that affect the number of, what affects the number of text you can store in an index?
Oh, the way, the name of that.
The way associativity, right? But does the code, but can a code change that?
Oh, no.
Right, so that's probably not the right reason, right? Yeah, but thanks for your opinion. David, do you want to follow up with that?
Yeah. So we think it's conflict. It reduces conflict miss because if you look at the block algorithm, every single time we're accessing like only like a local memory, so that we're accessing like a local memory. So the
What do you
chances
mean by local memory here?
So that like because if you look at the naive algorithm, right, like we're accessing like A from the let's say what is A? A is from the I think it's
Well,
from the
say it's 2K, right? You can put a number, right?
yeah, no, I'm saying it's from the it's from the rows, right? A is from the row, like you access it like row by row, and then B is like you access it column by column. So if you're let's say like if your column is like really big, and sometimes your column it will get overwritten because your set your set associative is much less than your column size.
Right. So for Intel Core i7, right, as far as you remember, we only have 8 different ways, right? So, and for blocks within the same index, you can only put 8 of them at most, right?
Yeah.
Okay.
So, but for block, since your the like I guess the each block the size is like much smaller, the chances of getting overwritten is going to be small. So like you can
Is it because the block size gets, well, I still don't quite get this part, right? So when you say is it why it's related to the removing of conflict misses? So so here your point is that, well, we can have we only have 8 ways, so we cannot accommodate this many blocks, right? So how does the algorithm help that?
Because we have a like each time we're accessing like a smaller block.
Yeah, but when you say smaller block, is it the cache block or is the block in your matrix?
The block in the matrix.
Right, and when you say small to what degree?
I guess to the factor of n.
To the factor of n, right? So one thing that you find interesting is that when I test 248, I actually divided by 128, right? So it's actually 16, right? So What does that mean? I'm only restricting my access to 16 different blocks, right? So, and if we are lucky enough, then the index keeps growing, there's no overlap, is possibly that the A-way cache will probably not use out, right? So you can reduce the conflict misses.
Yeah.
And what's the other thing that we try to remove?
Say capacity miss.
Right. In the meantime, right? Like if I divide it by 128, right? Which means that every time I'm only accessing 16 elements, right?
Right.
And for 16 elements, 16 by 16, and times 2 times 8 bytes, right? It turns out it's only 256 times 16, right? So it's only 4 kilobytes, which is way smaller than your cache size, right? Your cache size is 32K.
Yeah.
Right. So it also reduced the capacity miss, right? But remember what we mentioned in the previous slide. Simply a row itself is already 16 kilobytes, right? So it's very unlikely that your cache can hold all of them. So the block algorithm will help on both. All right. So thanks for Team Red for your insights. Now, these pieces of code, so thanks, David. And this piece, well, so now in your homework, you are probably familiar with these pieces of code called matrix transpose. So matrix transpose, you are probably familiar with the cache behavior as well, that, well, it's also not very cache friendly. And for the block algorithm, now one thing I want to try is that if I add matrix transpose in before having a matrix multiplication. So it seems like, wow, you are adding more instructions into the code. It seems like counterintuitive for performance. But now I want to show you it may be different from what you think. So here I have a matrix code BT, which I have a matrix transpose code here that I try to transpose B to BT. And when I do the block MM, I also implement a block MM transpose code that perform matrix multiplication on the order of transform the matrices. So that my index would, instead of the original implementation would be KK, JJ, but now I can make it JJ and KK because it's already transposed. So let's see what the performance of the matrix transpose code looks like. So remember, we were at, for 2K by 2K matrices, we were at 5.6. But now with transpose, here is what our performance looks like. It's reduced by 10% more. It's only 5 seconds, right? And if you don't believe, let's run the 2K by 2K case again with the same parameter. So now let's run the 2K by 2K case again. It's going to be 5.7, and maybe we can change the partition a little bit and see what the performance would change. And turns out, well, it's going to be better. But trust me, if you use the same parameter for block MM with transpose, it's going to be even better. It's only 4.6. So for this, you should trust me that the adding matrix transpose would consistently improve the performance of your block MM further, even though it seems like there's an overhead there. So now I want to ask you, what kind of magic behind adding matrix transpose, although it seems counterintuitive? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looks like it's a good idea to have group discussion. So why don't you guys go into group and discuss? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I saw David, you raised your hand. So can you share your thoughts with us?
Yes. So our group, we decided on C, conflict
Okay.
miss.
So why is that?
So so it reduces conflict miss because by performing a matrix transpose, we're also accessing B row by row, which is nice because if you access a column by column, each time you access a new column, you have to like load that block, load the whole block into the cache again, but you're only accessing one element. But if you
Right.
but if you do a row by row, we can so if you do like 1, 2, 3, 4, 5, 6, 7, 8, we can access, like we can always hit the, we can only need to access I guess store the first block, store the block, and then access it like each element inside. So it reduces a lot of the conflict miss because we don't need to like load and unload a lot of times.
Right. So the main thing is that because every time when you access even though it's small amount of columns in a matrix tile, right? It could be more than 8. And
Yeah.
who knows if they are going to be creating conflict misses, right? So the best thing to do is that let's just avoid this, right? And the fewer amount of blocks that you would need each time, it would reduce the amount of conflict misses you have. So that's why the answer is C. Awesome. Okay, so thanks, David, and Group Red scored 2 this time. All right, so now let's talking about data structure. So Yeah, I talk about algorithms, right? And when I talk about algorithms, I'm not talking about those algorithms like dynamic programming or whatever. I'm talking about algorithms that are efficient. And for data structure, I'm also talking about data structures that would be efficient for code implementation. So let's start with this guy. So not sure how many of you are familiar with SQL query, but if today I want to create a database system that most of the queries are similar to taking the assignments from every student and count the average from the table. Which data structure here would you think would be more efficient? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so it's almost like 50 to 50% now. So how I guess the best thing to do right now is to have group discussion. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so it's still interesting. So 47% to 47%, 14 to 14. So it's a tie. So can I have some of the group share your thoughts with me? So I already see David. So Team Red.
Yeah, so we think B.
Okay, so is there any other group think it's A? If you belong to such a group, okay, so I have Kayat. Your group thinks it's A. Hello?
Yes, yes.
Okay, so
okay.
both David and Kayat are mute. Can you both like state why your group think it's that? Well, so let's start with David.
Okay, so I guess the difference between A and B is how how the table is structured. So for A, the table is structured like student wise, right? So so I suppose so like the average is like so you have each record correspond to a student. So if you wanna access the average of assignment 1, you have to go through like each record, and then you have to find their score for each assignment. So you have to do like a double pointer access, memory access to get the grade for each assignment, and then you have to compute the grade the average of those grades. But for B, since we know that it's I assume this average array, or like this pointer, is pointing to an array with like the average of the assignments. So we just need to access I suppose the first element in the average array for B, and then
So we are actually trying to count the average of assignment and put it into the average.
yeah. So I guess for B, you just need to access the average array, and then you can access the first element, and then you get the average. So I think for
assignment, all right.
yeah,
Assignment.
so I think for B is just one memory access. It's much faster.
Okay, so Hayat, what do you think?
Yeah, I think the group was discussing something similar. We chose A. Yeah, because so my group members thought that it probably utilizes spatial locality more.
Yeah, but in what way?
I'm not too sure about that.
Okay, so let me show you another demo. So that's in my structure. Okay, so here I have two different pieces of code. One is array of structures. Let me see. Okay, so this one is similar to the version A, where each student has his own or her own or their own struct of records. And each of the record contain ID, student ID, a matrix, or say an array of their homework score, and an average, which pretty much similar to the code, to the structure of version A. So in this one, if I want to perform the query like this one, I want to select the average of assignment 1 for everyone, all right? So it turns out what happened is, if I want to count, if I have this amount of students, if I want to count, sorry, this is probably this. If I want to count the average of each homework, which is the query that I'm doing, right? What happened is that, saying that if now I'm counting homework 0, I want to get the average of homework 0. I have to go through every student's homework 0, and then I have to count I have to fetch the data and count the average of their score. So that's the code, right? So, and if I have object of arrays, right, which is essentially the version B, what happened here is I want to count a specific homework, then the average of a specific homework for all students. Then turns out what I need to do is that I just count each column, each row index stands for a homework item, and J stand each column states for a student's homework of assignment I. Then my traversal is like this, right? So this is how I count the average of each homework item, which is implementing the select of statement of that database query. So now let me run these pieces of a code and show you what the performance difference looks like. So let's say I do array of, everything. Okay, so let's say I run the array of objects, which is version A first. And let me see what's the argument I have. It has been a while since I run this, so I have some. Okay, so if I'm running student average, so let me do this. So let me count object of arrays. So here, since we are not doing student average, we are doing homework average. So I should set this to 0. And let's say, let me run a default. Okay, I want total number of students. What's the total number of students I need by default? Okay, so saying that I have this amount of students and I have 10,000 homework items. Not sure if you guys are getting. So this is object of arrays, which is the giant data structure we have. Now let's run array of objects, which is version A. And object of arrays is version B. See? So for object of arrays, which is version B, it only takes about 3 seconds. However, if you do it in the array of object 1, which is version A, it takes 9 seconds. So it's a lot longer if you do it in an opposite way, right? So most of the time, from the software engineering's perspective, object orientation programming would tell you A is a better option. However, in terms of performance programming, B is a better option because, as many of you have discussed, for these pieces of a code, if all I want is count the average of assignment 1, or assignment I, then turns out, as you can guess from these pieces of a code, the locality of go through this array would be a lot better if you can traverse your array element in this way. So that's why people typically, when we implement database systems, right, we typically do column store rather than row store. So what does that mean by column store and row store? So given such a database table, most of the time you might think my computer would store data in this order. Like I store 110 Smith Joe 40K first, right? So this is what you would think. And typically most of the time when you use like CSV or Excel, this is how we store data. However, as most of the database systems try to use select column from a table, the row store is actually very inefficient. And as the demo that I just showed you it's 3 times slower. So in fact, most of the database system, high performance database system, all the SQL system, they use so-called column store. which we store data tables using column by column. So instead of store data records like this way, we store data records like this way. So how many columns you have would determine how many data stream you have. And each data stream would be maintained in the order of the record you have. So that's how we do column store nowadays. And that's how your data are stored typically in database systems. So it's pretty it's not very trivial. However, we chose to do this because it's more efficient. All right, so that's something about data structure. So data structure matters. Now, another thing that I want to introduce, another technique I want to introduce is called prefetching. So, so far we talk about conflict misses, we talk about capacity misses, and some of you might be thinking about, for compulsory miss, is there a way to remedy it? And indeed, there are software techniques that can help to remedy the compulsory miss. That's called prefetching. So this is the idea of prefetching. So saying that, I have this pieces of a code, and typically this is what will happen, right? So whenever you access D0, you will trigger a compulsory miss because we never visit D0 before. And then you will have misses like this. And then every time when you have a miss, remember we fetch a whole block. So here we got D0 to D7, and then we return the whole block, and then we resume the execution. And now everything will be a hit until we meet D8, assuming this is a double precision array. Now, when we meet D8, as many of you know, we are going to have another miss. And every time when we have the miss, we have to wait for the whole block to come back and start executing, right? So that's the original idea of cache misses. And so this one, this D0 and D8, we thought it's an unavoidable compulsory misses. However, if you can fetch the other block ahead of time, you may be able to avoid that miss when you access the data. So for these pieces of a code, we can easily guess according to the loop. It's very likely we are going to access D8 as well when we see D0 is accessed. So what would happen is that when we have the D0 missed, we also issue another spatial cache access request called prefetch, which tells the cache, can you give me not only the block containing D0, but also the block containing D8. Again, because the cache can only serve one request at the same time. So first of all, we would give you D0 to D7. However, in the meantime, when we start to work on elements like D1, the cache can start serving the miss between for the block containing D8 to D15. So in this way, when we read D8, there is a potential that the block containing D8 to D15 is already there. So this is how we can avoid or how we can further reduce the compulsory misses in the code. So there are several ways of prefetching, and in fact, modern processors like Intel processors, they have hardware prefetching. However, as a software programmer, you better know your application behavior better. So you can also try to perform software prefetch that is basically load data into some register that won't affect your computation result, or you can use prefetching instructions. So for example, in x86 instruction set architecture, you can manually insert prefetch instruction, and GCC can sometimes also do prefetch loop arrays to automatically insert software prefetching instructions. So now I'm going to show you another demo, which is for the matrix transpose code that you played before, like this. I am trying to insert a prefetch instruction when I am accessing a block. So this is another version, highly optimized, a highly optimized blocked matrix transpose code. And for this pieces of a code, what happened is when I am accessing a block of matrix to transpose, I start to fetch the next row of the block of data that I want to transpose. So that's my code of prefetching. So now I'm running these pieces of a code on on an AMD processor and see how effective is that. So let me make clean and make, and now let me see. So this is the, let me see what's the default dimension. Okay, so now let me run the transpose. So for the transpose code itself, it takes 1.8 seconds, and the data transpose part takes 0.72. So now if I add prefetch, let's see what happens. So if I add prefetch, as you can see, right, the times spent in transpose is improving by about 10%, right? So that's also, so that tells you that, well, with prefetch, with the compulsory miss further removed, we can actually improve the performance. We can further improve the performance of matrix operations like this, right? So now you can imagine, wow, for the matrix multiplication, we actually did a lot of stuff, right? We first blocking algorithm, we add transpose, and now I'm even showing you, if for the transpose, if you really want to improve the compulsory misses, you can also do prefetch. All right, so now I want to ask you, if you are a programmer, how many of the following code do you think you can use prefetching to effectively help improving performance? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so for this question, I do see we probably have better to discuss. So why don't you guys start the group discussion and come back in 2 minutes. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the voting result, it looks like most of groups reach a consensus. So, David, what does your group think?
We think only one of them is correct.
Okay, which one?
Number 2.
Number 2. And why others doesn't work out?
So for the first one is apparently this node is it's like a linked list structure. So since the memory blocks is not contiguous, so I don't think the prefetch will help because I don't think the cache knows what to prefetch. Yeah, because it's like the nodes, like the linked list could be everywhere in the anywhere in the memory.
And the other thing is that, right, considering the latency of fetching a missing cache block, right, you need to cover like tens of nanoseconds of latency, right? And for the linked list traversal, to get this, you already have to spend tens of nanoseconds, right? So even though you can be a little bit ahead of time, it's not sufficient for you to cover that latency, right? So this is not going to help.
Yeah.
How about the second?
The second one works because it's accessing like the I is like incrementing one by one.
Right.
So it's so we know that we can just prefetch the I guess the every 8th one, or dependent on your cache block size.
All right. How about the third one?
The third one is similar to 1. The root, I think, is also because it's like left and right. I think it's also like a linked list structure where you
Yeah. So the thing is that, right, like in your data structure class, we spend a lot of time to make sure that you know how to implement this, but in terms of performance, they are terrible. All right. So how about the fourth one?
Yeah, the fourth one, judging from this mixed I, like we thought about like, oh, since it's like 167 and like 13, they're all like kind of like prime numbers. So it seems like a pseudo-random kind of like mixed I is like acting some sort of like pseudo-random access. So I don't think prefetch would help here because we're accessing in like a random way.
Okay, so perfect. So I hope other groups has been convinced with this answer. And in fact, the answer I have for this question is the same with what David said, right? Because it's for prefetch, it really needs us to find a way to predict or to know what's the next element to fetch to do in a very, very easy way. So if you have a fixed length, fixed stride, then it's easy to predict. Otherwise, it's difficult to make the prediction. So that's why only one of these 4 examples, and in fact, 2 of them are very frequently used in your data structure class. And in terms of memory performance, they might be really bad. So hopefully that would give you some kind of inspiration about how to optimize the software for memory performance. So first of all, carefully lay out your data structure, make your data structure align with the access pattern, and also algorithm can be more cache friendly. So that concludes our optimization part. So now let me show you another aspect of memory systems. So let's look at this pieces of a code. So for this pieces of a code, what it's basically doing is that I am trying to count the average data within average values of a big matrix. And this matrix could be really big in a way that the dimension could be a variable. So saying that right now, if I put this default as 32K, right, then 32K by 32K, and given this is an integer, oh, sorry, so A is a double, right? So double means 8 bytes. Then this 32K by 32 is actually going to give you 8 GB of data. So now, if I have a machine with 32 GB of memory, if I have more than 65K elements per dimension, which means that I'm going to consume 4 times more space than this one. It's easy to consume all my 32 gigabytes of data. So now I do have a machine with here I have 3M. Okay, so this is a machine with 32 gigabytes of data. And now I am running this. Wait. Oh, okay. So now I'm running these pieces of code, which is exactly the same as what I showed in the slide. And what I'm going to do is that for the memory allocation, I'm going to run 64K, which in another screen later on, you will see is going to consume a lot of memory for these pieces of a code. And so now I'm start running these pieces of a code, and as you can see, right, the virtual the address is the memory is going to consume about 32 gigabytes. So I want you to tell me what would happen. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so definitely I think we need a quick group discussion. So let's go. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so David, Team Red 2, you have it.
Oh yeah. So we think we decided on D. The program will
Okay.
finish without any issue.
But why is that?
So I think in OS class we talked about like the idea of like virtual memory, right? So the idea of like how the OS, like if you like, despite the limitations of like physical memory, the OS will like try to take care of like um your um your memory allocation and try to like create more space by toggling between the disk and the memory.
Okay, so let's see what happened on the side. So indeed, the program finished without any error message, right? So yeah, there is not really a error message here related to the program that we just run. So you are right. And indeed, the program finished correctly without any issue. So, and you are also right, it's related to something called virtual memory in both architecture and the operating system we try to maintain. And tomorrow we are going to focus on this. But before you leave the classroom, there are several things that I want to remind you today. So first, we have assignment 3 due this Wednesday, and it's made as an online exam on Gradescope. So you don't have to download any PDF. Instead, it will be made as an online assessment, online exam format. And the reason why I intentionally make it this format is because this is exactly the format you are going to have in your midterm. So good thing or bad thing. So the Gradescope actually allow you to use markdown syntax and a LaTeX equation formula to describe your answer. However, if you are not familiar with that, please go through these 2 links, these 2 documents to learn how to use it before the midterm. So that's why I set up this assignment this weekend to make sure that you get a chance to get familiar with it before the midterm, and you definitely want to get familiar with it before midterm occurs rather than looking up the syntax or looking up how to use it during the midterm. And regarding the midterm, a lot of you care about this. And again, I just noticed that on the same day we have discussion session, and I don't want people to discuss the midterm question during the discussion session. So it will start after the discussion session until Thursday, 3:20 p.m. And you will be able to choose any 18-minute slot consecutively. Make sure that you have no internet issue at that time. And remember, TAs, instructors, we are not 24 hours, 7 days. So if there is anything occur during the late night, we are not going to provide help. And in fact, to make it fair, we will provide no help during your during the time frame of midterm. So don't post anything on Piazza during the midterm. If you do, it's treated as cheating. And to prepare for your midterm, you should at least review slides, your reading quizzes, and your assignments. And it will cover topics up to this Tuesday. And you should also focus on the materials, especially covered again and again in both of these materials. And some of you were talking about we don't respond to Piazza. So the thing is that it's not true, and we tried our best to respond. But the thing is that we are not working 24 hours, 7 days. So we do need our time to stretch, to take rest. So sometimes it's, especially weekends, don't expect us to give you very, very fast response. And I have already tried to tell our TAs and tutors to respond as early as they could, but I cannot control everyone, and I am really limited in my energy, especially this weekend. I'm working on your midterm, so I don't have time pay attention to every of the posts. So Another thing that I want to tell you and convey to you is that the following labs, they are really time consuming. So please start early and don't expect the last minute help would change things, and don't expect the last minute help would be really helpful, because we are really short on our energy and resources. Hayat, questions?
Yeah, Professor, is the lab due this Friday?
There is a lab due this Friday.
Okay, so there's an assignment on Wednesday, midterm on Thursday, and lab on Friday.
Right, but if you pay attention to what I said in the lab, we don't have programming assignment this time. So at least go through the notebook. And the other thing is that the lab this time is highly related to your midterm. So definitely worth doing it. Other than that, if you don't have any other question, enjoy the rest of your day. I will see you tomorrow.
Hi, Professor. I have a question.
Yes, sure.
Yeah. So for the lab 1 grade, it says it's out of 10, but I think I don't know.
I fixed that.
Oh, you fixed it?
Yeah. I think
Okay.
I respond to your email already.
Oh, I haven't sent an email. I thought, oh,
Okay, so that's probably another people.
okay,
All right.
okay.
All
So,
right.
okay, thank you.
I've been told by
Yes.
Professor, so for the homework 3, is that like a preview for the midterm on this
No.
Thursday?
No. But it lets you practice the tool that we'll use for this Thursday.
Cool.
Okay.
Thank you.
Goodbye.